Hello everyone. In this video we are going to discuss one important theorem, the simple approximation theorem. In this theorem says that an extended real valued function f on a measurable set E is measurable. And measurable set E is measurable if and only if there exists a sequence phi n of simple function on E which converges pointwise on E to f, and which has the property modulus of phi n is less than or equal to f on E for all n. Suppose if f is a non-negative functions, we may choose phi n, the sequence phi n is the sequence phi n of simple function to be must be an increasing function. One part is we can easily prove. Because already we know that each simple function is a measurable function. And also we assumed that f is a pointwise limit of a sequence of simple function. Also, if f is a pointwise limit of a simple functions, already we proved that in proposition 9. The proposition 9 says that if let f1 be a sequence of measurable functions on E that converges pointwise almost everywhere onto the function f, then that function f is a measurable function. Therefore, we get that f is a measurable function. Now we prove the converse part of this theorem. So we assume that f is a measurable function and also assume that f is a non-negative function. F is greater than or equal to 0, that is a non-negative function on E. In general, f is equal to f plus minus f minus, but f plus and f minus are non-negative functions. Therefore, f is also. Now, therefore, the result follows any f. Now we define the set En as set of all x in E such that f of x is less than or equal to n. We define En as set of all x in E such that f of x is less than or equal to n. How it is defined? E is a set. The f is a measurable function on E. And also assume that it is a non-negative function. It is non-negative function on E. Therefore, f has the values f of x on the codomain. Okay. Now define the function. Define the set En as. Define the sets En as, that is E1, E2, E1, E2 and some En as, that is the set of all x in E, set of all x in E such that f of x is less than or equal to n. Some n. And we assumed that f is a measurable function. Therefore, we get that En is a measurable set. That means f restricted to En is a non-negative bounded measurable function. F is a non-negative measurable function which is restricted to En. Therefore, we apply the simple approximation theorem on to f restricted to En. And we choose epsilon as 1 by n and select the simple function. Therefore, we select the simple function phi n and psi n on En by phi n is greater than or equal to 0, which is less than or equal to f, and which is less than or equal to En on En. And phi n minus psi n minus phi n is greater than or equal to 0, which is less than epsilon. Here we take epsilon as 1 by n on G. So we observe that phi n is greater than or equal to 0, which is less than or equal to f, and we get that f minus phi n is greater than or equal to 0 but less than or equal to psi n minus phi n, psi n minus phi n, but which is less than 1 by on G, but which is less than 1 by n on n, but which is less than 1 by n on n. Now we extend, so it is defined on phi n is defined on, sorry, phi n is defined on en, phi n is defined on en, okay, phi n is defined on en. Now we extend phi n to all of e by setting phi n of x equal to n for f of x is greater than or equal to n. We define the simple function phi n of x equal to n if f of x is greater than or equal to n, f of x is greater than or equal to n, because f of x is, therefore we define a simple function phi n and psi n. We define this simple function and less than or equal to psi n, less than or equal to psi n. Therefore if f of x is greater than n, suppose f of x is greater than n, we take phi n as phi n of x equal to n if f of x is greater than n. Therefore the function phi n is a simple function on E, and phi n is greater than or equal to 0 but less than or equal to f, which is less than or equal to psi n on E. Okay, now we claim that the simple function converges to f pointwise on E. So we take x is an element of E. So we take the two cases. Suppose we assume that f of x is finite. Suppose f of x is finite, then we choose a natural number n for which f of x is less than n. What it means that is en is equal to E and en plus 1 is equal to, because it lies outside en. Okay, therefore we choose a natural number E, capital N, for which f of x is less than n. Then f of x minus phi n of x is greater than or equal to 0 but less than 1 by n for all n is greater than or equal to n. Therefore we apply the limit n tends to infinity, we get that which is equal to 0. Therefore limit n tends to infinity f of x minus phi n of x equal to 0. That it means limit n tends to infinity phi n of x equal to f of x when f of x is finite. Suppose we assume that f of x is an infinite set, then phi n of x equal to n for all n. Okay, therefore we apply the limit on both sides, we get that limit n tends to infinity phi n of x equal to f of x. Now we replace phi n of x, the maximum of phi 1 phi 2 phi n, we get that phi n is must be an increasing function. So okay, thank you.